Good morning, everyone. I am Lincheng, coming from School of Astronautics, Beihang University in China. It's my pleasure to be here to apply for the Best Research Award in the International Research Awards on New Science Inventions. I will introduce myself and my academic background first. I got my bachelor's degrees and a PhD at Beijing Institute of Technology. Now I am a postdoctoral researcher in Beihang University. I have three important international experiences, including 1 year in Polytechnico di Milano, 1 month in Israel Institute of Technology, and 4 months in Technical University of Munich. My professional experience includes currently I am the principal investigator of three programs. I have published one monograph, obtained one provincial award, and published 4 SCI journal papers, 5 EI conference papers, and 8 authorized patents, obtained 2 competition awards, and have already made one invited speech. My academic background is about can be described by 3 keywords. The first one is geosynchronous orbit, which involves geostationary orbits whose inclination is 0, and the inclined geosynchronous orbit. The second keyword is the GSO spacecrafts, whose advantages include high cost, high power, high lifespan, and high precision. To make a better usage of GSO spacecrafts, we developed all electric propulsion technologies, which is significant savings in fuel and give a important reduction in the load. All of them are combined to give key technologies to utilize the high orbit resources. The typical geostationary satellites includes Gaofen 4 and Fengyun 4 made by China, and the typical satellite constellations in the inclined geosynchronous orbit are the Beidou 3. Currently, different countries has developed different all-electric platforms, but there are still some distance between the all-electric platform made in Europe and USA and that in China. They are playing important roles in communication, navigation, remote sensing, and many fields, providing economic benefits to all the operators. On the other hand, with the increase of space launches, which led to a debris populations in the geostationary region, now the government and the researchers are all focusing on the sustainability of the space environment. Thus, I focused on 2 regions. One is the geostationary region and one is about the inclined geosynchronous region. And there are 2 important dynamic behaviors. One is station keeping, which is used to confirm the normal functions of satellites. And the other is the end-of-life disposal, which help avoid the satellites becoming the space debris. Here, we give some typical missions in the geostationary region. They are Telsat in Europe, made by Airbus, and the Shijian 3 made by CAST, and the HipSat by OHB Company, and the ABS-3 by the Boeing Company. The important conclusion is that they all provide alternatives to deal with limited operational slots, and they are required for higher precision on-orbit service. As for the typical missions in the infinite geosynchronous region, currently from several decades, we have serious constellations by USA, quasi-Zenith satellite system by Japan, and Beidou 3 by China, and Indian regional navigation satellite system by India. They all provide an extension of the global navigation satellite system, but they are also used to replace the role of geostationary satellite. This is the motivation and the initial goal to develop such kind of satellite constellation. Here we give some comparisons about electric propulsion and the chemical propulsion, as well as the low thrust station keeping and the impulsive station keeping. For the electric EP, they have low thrust magnitude, high specific impulse, and low fuel consumption, while the chemical propulsion CP has low launch cost, but can obtain more payloads. And the control periods for low thrust and impulsive, one is 1 day and the other is 2 weeks. And as for the accuracy, of course, the low thrust station keeping can obtain higher accuracy since they provide lower thrust. Thus, we can get some conclusions. All electric platforms act as enablers for innovative exploitation of space, and we need to employ maneuvers to eliminate drifts caused by perturbations. However, control in a daily basis will definitely increase the operational cost. Thus, we need further exploitations about the perturbations and the no-thrust maneuvers. Then come to the main research of myself. First is about the orbit dynamics for the whole GSO orbit. We derive the semi-analytical propagator in the first step, which analyze different terms of different periods. So we can choose single averaged, double averaged, or triple averaged for different missions. And we developed the long-term filtering orbital propagators, which involves the system and the measurement equations. And we use Monte Carlo method to calculate the covariance matrix. And we need to choose different filtering algorithms for different cases. First, we will consider that the mean orbital elements are throughout the short period information, and the linearization for the system and measurement equations will throughout the high order terms, so that the analytical Jacobian matrix will be the key to improve the filtering precision of the algorithm. So we can see a simple workflow of the filtering algorithm. The key is to calculate two Jacobian matrices. The first is for the state equations, and the second is for the measurement equations. They have simple matrix form like this, and the extension and the detailed expression about different terms, you can search it in my publications. We also analyze the geosynchronous resonance. One resonance is coming from the Earth's traxiality, so we use Delaunay variables and the Hamiltonian functions to describe these resonances. You can see it here in the east-west station keeping. Once we consider the ideal tensor resonances, we can get 4 equilibria, 2 kinds of manifolds, and the whole phase space is axis symmetric. As for the complex tesserons resonances like the J33, J44. Once we consider that, we will find the phase map is asymmetry and there are some chaotic regions appears where the satellites will move around either equilibria in a random way. As for the resonances led by the unisolar perturbations, we also use the dynamic equations to find the resonance map. The key characteristics is that there are two main kinds of manifolds, and we can also use this phase plot to explain why the geoprotected region was defined in the ranging from 0 degree to 14.6 degree. There we also provide some simulation results to validate the efficiency of our propagators of our filtering algorithms. First, you can see it here. You can choose different periods of propagators such as single averaged, triple averaged, or double averaged here according to the real requirements of the space missions. Here, we also do some orbit propagations with maneuvers. You can check it here. We can get a very nice long-term behaviors. As for the robustness analysis, we use small arrows and big arrows, and all of them will be moved out within 300 seconds and 600 seconds respectively. As for the application in the whole GSO region, we choose 365 spacecrafts and conducted a 100-year simulation run. And all the data sources are coming from the opened ESA's reports, the classification of geosynchronous orbits, and the results is wonderful. All the main orbit elements are within the expected region. The third chapter is about the low thrust control for the spacecrafts. First, we derive the minimum time and the minimum fuel model. They conclude state variables, throttle factor, thrust-related coefficient matrix, perturbation-related coefficient matrix, and thrust unit factor. We also put the objective functions and the Hamiltonian functions here. To solve the Hamiltonian function with the principal maximum problem, we also derive the optimal thrust unit vector, the switching function in different expressions, and finally we get the two-point boundary value problems with some constraints. Here, we give a detailed analysis about the constraints we considered. The first is about the thruster configuration. Here, we give a comparison of the 4 thruster configuration and 6 thruster configuration. One is for the minimum mass principles, and the other provides a backup of the thrust friendliness. So they have different usage. They can be maintained in different missions. The second constraint is about the station keeping and the angular momentum combination. We derived the single thruster's angular momentum and the total angular momentum. Finally, we can get 7 equality constraints and 8 inequality constraints. The third constraint is about the station keeping slot. We can see here the slot in the east-west phase space and the north-south phase space, which can be expressed as the following equations. And here is for the inclined geosynchronous orbits. The station keeping slots are more considered in the eccentricity vector. And here is the expressions. The chapter 3.3 is about the initial co-state guess, which provides efficient convergences for the whole indirect optimization. First is about the initial co-state guess for the geostationary region. We have three steps. All of them are based on a two-impulse solution and a special point coming from the continuous thrust arc, and we can get the middle point to do the initial guess. As for the initial guess for the inclined geosynchronous region, the method has been extended into a four-step method, and which is based about the three impulse solution. Once we got three impulse solution, we can divide the whole orbit into three arcs, and according to the variation of the carriage speed, we can use the middle point in the major arc or the minor arc to get a better initial co-state guess. As for the solution space, all the work above is about the single solution. And this year, we find some connections and interesting phenomena about the solution space, which concludes all available solutions for the low thrust transfer problems. And the main contributions of our work is that we provide longitude homotopy via a continuation on the final longitude, and we found a bonded and a smooth solution surface. And based on the solution surface, we provide the thrust net longitude combined homotopic approach and a new hybrid approach to find a solution from an existed solution to the global optimal solution, which give a very clear and potential ways to know why the solutions can be connected and why we can improve the performance of this method. That's the benefit. We give a really analytic alternative for all available solutions. Here we also provide some simulation results. The first one is about the thrust sequences and their allocation in the polar phase. The second is about the closed station keeping track within the east-west station keeping slot and the north-south station keeping slot. Here in the east-west phase, we have a bow shape, and here we also have a bow shape, but the direction of the bow is different. And here is a three-phase plot about the 3D plot about the closed station keeping track. Here we also give the low thrust arc allocation in four phase space, and this simulation is about the inclined circular orbits. The first one is in the radius phase. The second one is about the longitude phase space. The third one is about the latitude phase space and the closed station keeping track in the eccentricity vector. We also show some fast re-entry chances. Here you can see according to green lines and two red lines, we found a square which can help the currently in mission satellites to a better re-entry orbit. That's all for my presentations. Really happy to be nominated for this